Hello, everyone. I'm Charlie Sharpless, the Assistant Director for Research at Princeton University's Untitled Center for Energy and the Environment. I'm pleased to welcome you to the final talk in our summer seminar series, New Light, Rising Stars and Energy and the Environment. This series has featured weekly talks by early career researchers working with faculty at the Untitled Center, where our mission is to develop practical solutions for a sustainable energy future. Reflecting the transdisciplinary nature of this mission, the New Light seminars spotlight the next generation of leaders from a diverse array of fields, including engineering, energy systems, material science, social sciences, public policy, and more. We're excited to host these outstanding scholars and bring their work to you through this series. Before continuing, please note that if you have questions during the talk, feel free to type them into the Q&A box. At the end, we'll also have the raise hand feature enabled, which can be used during the Q&A session when we'll address as many questions as possible, beginning with those submitted during the talk through that Q&A box. Today, our speaker is Dr. Melissa Ball. Dr. Ball holds dual bachelor's degrees in economics and political science from the City University of New York and the University of Georgia. She also holds a master's degree in political economy from the London School of Economics and Political Science, and a master's and a PhD in chemistry from Columbia University. For the past few years, Dr. Ball has been appointed as a presidential postdoctoral fellow at Princeton, working with Professor Lin Liu on the design and synthesis of organic and perovskite materials for photovoltaic applications. Unfortunately, Professor Liu was unable to join us for today's talk, but another of Dr. Ball's Princeton collaborators, Professor Antoine Kahn from the Department of Electrical and Computer Engineering at Princeton, has kindly agreed to provide the formal introduction. Please join me in welcoming Professor Kahn, who will introduce Dr. Ball.
Thank you, Charlie. Good morning, everybody. My name is Antoine Kahn, and I'm a professor in electrical engineering, electrical and computer engineering, and also the vice dean of the School of Engineering. And it is also my pleasure to introduce the speaker today, Dr. Melissa Ball. Charlie already gave a little bit of her career path, which is quite extraordinary for a research scientist. She, as you heard, started in a different direction in economics and political science. And when I met Melissa 3 years ago at a Gordon conference, we talked, and I was particularly interested by somebody who had such a very diverse background, a very interesting background. She was finishing her PhD at Columbia University at the time, and I suggested that she come to visit in Princeton, and she came and then applied for postdoctoral position. As you heard, she received, or she was accepted as a presidential postdoc at Princeton, and has been working in the group of Professor Lin Liu since. Melissa works in the intersection between the structure and function of various materials, but in particular organic molecules for application in organic electronics, as well as these new materials called metal halide perovskites. And we have started to collaborate a bit, and I really admire her work. So it is my pleasure to again introduce her for this talk. She is going to talk about molecular design for emerging solar material. So Melissa, please.
Thank you very much, Antoine and Charlie, for that introduction. I remember that visit very well to come to the Interlayer Center into Princeton. And I knew when I first came that this would be my next home. And so let me begin sharing my screen. And let's see. Perfect. So I'm really happy and excited to be here this morning, to be the last presenter for this wonderful summer series, and to talk about my work in the Liu group here at the Interlayer Center for Energy and the Environment on the molecular design for emerging solar materials. And so I want to begin with basically whether you're at the director level or you're in the laboratory like myself, and what is our, I guess, the motivator across the Andlinger Center. And it's really this question of how can we create a more sustainable energy future? And as many people on this call will understand is that basically when we look at the energy diet, and here I'm showing the United States in percent of kiloton of oil equivalents, we can see that our energy diet is basically fossil fuel based and natural gas. So the reason this is an issue is that oil, natural gas, and coal are the largest percent of our CO2 emissions. And so when I see this slide and I think about the left graph in particular, I really see an opportunity, and that opportunity lies in renewables. And so here at the Andlinger Center, the Net Zero America project has modeled pathways where we can get to net zero by the year 2050. And my key takeaway when I think about these different scenarios, when I think of the annual generation by these different energy sources, whether that's wind or solar or hydro, is that there's a really large demand or requirement for wind and solar. So even in the more restricted case, where this would be this RE minus case, these wind and solar would need to supply 44% of our energy generation in order to meet this important target. And in cases where we do not have restrictions on renewables, they can meet up almost to 100%. And so this is such an exciting time to be working in solar energy and to be thinking about it. And it really shows by these different 5 scenarios that solar energy has a really large role in helping us meet these our goals by net zero by 2050. And so when we think about solar, so what is the current state? So silicon really is the workhorse in the solar industry field. And so here I'm showing a beautiful picture of a solar farm. And so the question is, well, why? And so silicon is efficient, it's cheap, reliable, abundant, and scalable. And so that makes it a really great material to use for broadband absorption. So when I think about solar, there were a couple of questions that I was thinking about, and that is one of them is, can we develop technologies that can supplement silicon? So the previous slide showed that we're going to need mass deployment of solar over the next couple of decades. And so in that market, there's surely technologies that as basic researchers in the lab that we think about, could they supplement silicon in order to meet that deployment demand? And also, are there markets that silicon cannot easily address? So these niche markets, so application-based solar. And so with that, so Antoine and Charlie mentioned my trajectory. So I was a graduate student at Columbia in synthesis. And so I really thought a lot more about molecules. And so for those that are not so sure about what that would mean, it's really thinking about taking 2 things. I'm gonna call these components A and B. And how I think about A and B is like I think about their light absorption, their energy levels, their energy gap, even their interactions with one another. And can I synthetically put A and B together to make, let's say, this green molecule here? And then what kind of absorption does that have? So here I'm showing intensity versus wavelength, the schematic. And likewise, if let's say I want a different application, and so I need a different molecule, an organic molecule to meet that application based off absorption and energy levels, then one could think about C and D, and again, using synthetic chemistry to put those together. And so I really loved being an organic chemist for graduate school. And so certainly in the Lou group here at the Andlinger Center, I've spent a lot of my time on synthesis, but also one of the most exciting parts of my postdoc certainly was thinking more on the devices and being able to learn about solar from a completely different perspective. But really, my goal has been to design molecules with specified properties that are application dependent. And so the first one of these projects I would like to discuss today is really in that first question I asked is about supplementing silicon. So is there a technology that we can develop as research? It's that's efficient, cheap, reliable, and all these things that silicon is, but also something that's broadband too. And so I will begin this talk with talking about our work in the Lou group on 2-dimensional perovskite solar cells. And this is with my colleague, who's also a postdoc in Lynn's group, Xiaoming. And on the second part of this talk, I'm going to talk about our work on developing transparent solar cells. And that's really to address that second question on, can we target markets that silicon cannot easily access? And this work was in collaboration with my colleague, Quinn, who's also a postdoc in the Loop group. And so beginning with two-dimensional perovskites, so I would like to first talk about their structure and what's important about that structure. So really, perovskites are these corner-sharing octahedra. And so the metal center here I'm showing with my gray circle is typically a lead or tin, and they're surrounded by a halide, so a chloride, a bromide, or an iodide, depending on what optoelectronic properties you would like. And so because I can't do 2D on the computer screen, just imagine that these corner sharing octahedra are going into the plane of your computer. And so these corner sharing octahedra are joined together by these large organic cations. And largely my work in the Loop group has been thinking about these organic cations, and in particular, these green circles on my schematic. So in order to understand how we can design better materials, we have to understand where those materials properties come from. And so in 2D perovskites, there's two things that we think about. So the first is in the in-plane direction. So imagine taking this inorganic octahedra and turning it 90 degrees so you can see the entire plane. You would have something that looks schematically like this. So this is called the octahedral tilt. So you'll hear me talk about this in the next few slides. So some materials have a larger deviation from 180 degrees, and they measured this by the metal, the halide, the metal angle. So this octahedral tilt here in my depiction is less than 180 degrees. And on the right side, I'm showing schematically a octahedral tilt that is almost in the ideal 180 degrees. And the reason this angle matters is that in 2D perovskites, that's really where the conduction band and the valence band reside. So we care a great deal about how these lead centers are able to effectively communicate with one another through their orbitals. And so that angle matters. The other structural property that we think about is basically how far away are inorganic octahedra from one another. So you can imagine that it's called interlayer spacing. So they could be a larger gap between those inorganic octahedra, or it could be a smaller gap. And this matters because if we think about transport, so if we have our electron or our hole and in solar devices, once it's residing on one of the octahedras, surely on the in plane, we can have delocalization, but what about the out of plane direction? So to summarize what this is going to look like, so we think about our two-dimensional structure. We have our octahedral tilt and interlayer spacing that I just mentioned, and those are really important parameters that feed into materials properties. And remember, our ultimate goal is we want to create efficient devices that absorb broadband as a supplement to silicon. And so we really care a lot about their band gap, their carrier mobility in particular. And so putting back in my schematics, the organic ligand, again, the part of this that I was thinking a lot about, there's a couple of things that one can consider. So if we first start on the top, in our organic ligand, a couple of things that matter. So how much this organic ligand, and in particular this ammonium terminus, penetrates into that inorganic plane matters. So it's best if you see it here where my pointer is, where this ammonium can be further in this A prime site. And if it penetrates further, then this ammonium is going to interact more with what we call the equatorial positions. So the equatorial is what I'm highlighting now. And then here, the equatorial would be this halide or this halide. And so this matters because if this ammonium wants to interact more with this equatorial position, it effectively can move it out of that 180 degrees. And that's what we're thinking about. Likewise, depending what's on your blue circle here, you could have a larger interlayer spacing, or you could have a smaller interlayer spacing. And so what I mentioned earlier about that out of plane direction, I think anecdotally for myself, I think more about the octahedral tilt, but there's certainly, as I'll show in a few slides, some correlations with materials properties in the interlayer spacing. And so this organic ligand's pretty nimble, and it can move and contort itself in order to both maximize the energy balance sheet between interacting with itself or not interacting with itself, and also interacting with the inorganic framework. And so the large question that I asked myself was, how does the organic cation influence structure? And so in order to tackle that question, let's break it down into 3 parts. So the ammonium, again, as I mentioned on the previous slide, it's going to interact with these halide positions. And that's really what affords this 2D assembly. So the ammonium is going to either interact with the axial position or, again, the equatorial position, or both. It doesn't have to be either or. And so that is really about this 2D assembly framework. I then really look at the linker. So often in the perovskite literature, to date, a lot of these linkers have been alkyl based. So alkyl just being carbon and hydrogen based. And that's really, I think from my perspective, is really endows the organic linker with flexibility and also stability. So 2D perovskites are more hydrophobic or resistant to water than their 3-dimensional counterparts. And that largely comes because these organic linkers are composed of carbons and hydrogens. And so this flexibility, though, really allows this ligand itself to contort and adopt non-ideal geometries in order to basically fit within this organic bilayer. And then the third part of this organic framework, which has been largely unexplored, and this is where we have spent most of our energy, is thinking about this, again, this purple circle. So, can we manipulate this purple circle on the non-ammonium terminus in order to affect structure? And so how this would work is that, putting on this supramolecular chemistry hat, I was thinking about, could we take some of the long lessons in organic chemistry and apply this to the organic ligand? So hydrogen bonding, halogen bonding, or pi-pi interactions, and many, many more. And so our hypothesis was this: can we install a moiety that replaces my purple circle that effectively wants the purple circles to positively interact, so come much closer together? So if we think about that in my schematic, where my pointer is if these purple circles want to come closer together, it potentially could squeeze those inorganic octahedra closer together, so reducing that interlayer spacing. But also, would it withdraw the ammonium terminus away from these equatorial positions? And so if it did that, then in turn, we would have less deviation in that octahedral tilt. So those 2 structural properties that I mentioned earlier. And so beginning with hydrogen bonding, we set out to design this experiment. So we picked 4 different organic ligands. So here I'm showing their chemical structures on the bottom, and I'll walk everyone through this. So here what I've highlighted is I've got a methyl group, so a CH3 group, and this is really our control. And so a methyl group interacting with itself is just going to be called dispersion forces, and they're not very strong forces in organic chemistry. But the other 3 ligands, we wanted to then install moieties that we thought could strongly interact with one another. So here from left to right, we have the carboxylic acid, a hydroxyl group, and a cyano group. And for those that are not used to this type of drawing for organic chemistry, imagine this vertex as a carbon atom, and off each carbon atom, there's 2 hydrogens. And so effectively, a cyano, a hydroxyl, and a carboxylic acid are able to do hydrogen bonding with one another. And so again, testing that hypothesis about these favorable interactions with drawing our organic ligand. So we were able to get experimental structural files, and then also working with Dr. Arvind Kakani and Professor Andrew Rapp at the University of Pennsylvania, we calculated their theoretical structural files. And so here I'm showing the theoretical structural file, and you can see that in this bilayer, the organic ligand in our control, they're basically extended out into the layer, and they're not strongly interacting. And when we look at our other 3 molecules that have this hydrogen bonding moiety on the non-ammonium terminus, we see a really different picture. So let's start with the carboxylic acid, and what we see is what we've called effectively a molecular zipper. So what it's composed of is that you have the proton-like hydrogen here that's on this nitrogen atom, and it is hydrogen bonding with a hydroxyl group across the organic bilayer. And these are very, very close, 2.4 angstroms apart. Likewise, on the other end, you also can see on the zipper, we've got the carbonyl with the proton on the hydroxyl. So the zipper feature was really nice and unique to see. And then if we consider the hydroxyl, So again, that alcohol, and then the cyano, we get a really even different picture. And so with the hydroxyl, it forms this like pseudo rectangular shape, which is really neat. And so again, it's composed of the ammonium hydrogen that is hydrogen bonding across the ammonium the organic bilayer to the hydroxyl group. And it's doing 2 of those per pair. And then we can see here in our cyano case, it's a really similar story, except now we have a pseudo hexagonal shape. And so we've got the cyano ligand that's strongly interacting with the ammonium across the ligand. And you can see here, it makes this really nice C shape that we were really interested in. And so with these different ligands, we were really excited to see that we could see very strong intramolecular molecular interactions between our organic ligands. And so we were first curious about the structural properties. And so looking at those structural properties, so in this table, we began talking about those 2 most important ones, so the octahedral tilt and the interlayer spacing. And what you can see here is I go through each of the ligands. So the trends are this. So when we go from our control, it has the largest deviation from that ideal 180 degrees that I mentioned earlier. But then as we go from our control to the carboxylic acid, to the hydroxyl, to the cyano, we can see that in the latter case, we're almost at that 180 degrees. Likewise, for interlayer spacing, we see a descending trend. So we see that we have in our control case, it has the largest spacing. And so remember, with that spacing, that all else being equal, the further apart those inorganic sheets are, the more hindered out of plane transport could be. And so what we see here is that we have in our control the largest spacing, then going down to our cyano case, we have by far the shortest spacing. And that's really largely an effect of that C shape that I mentioned earlier. So with these structural properties, we wanted to see how they correlated to the materials properties of these systems. And so Xiaoming measured their band gaps, and also he used SCLC to measure their mobility. And so on the x-axis, I'm showing that tilt. So again, that's structural property. And on the y-axis here, I'm showing band gap. And so what you can see is there's a nice linear relationship. So showing that the structure function is alive and well in these systems, in that in this point here, this is our cyano case, where it has the smallest band gap. And it also is the one that's closest to the 180 degrees. So just what we were, our hypothesis was true and what we were expecting. And so again, a smaller band gap is important. If you're trying to do broadband absorption, you want to absorb as much of that visible light as you can get. And so that cyano case looked really, really nice. And then if we contrast it to our control, which is all the way over here, we can see it has that largest deviation from that 180 degrees. And it also in turn has the highest band gap. We also plot mobility, the log of hole mobility for these systems. And we also see a linear dependence that our material that has, again, the closest to 180 degrees has the highest mobility. And then the material, so our control, the CH3, has the lowest mobility and also has the highest deviation. Looking at interlayer spacing, that second structural property that I mentioned, we see a very much a similar story. So the experimental band gap and log of hole mobility trend with what we were wondering and expecting is that the smaller that spacing is, then your band gap in turn reduces. So we see that these correlations between the structure and then the materials property are strong. And so when we, working with our colleagues, we basically thought about how to combine structure with the materials. We were really thinking about the length scale. So if we think all the way to our end goal of making devices that are high efficient, then we are really at this centi-to-milli length scale. But then structure really is about tens of nanometers all the way to, I mean, milli can be anything. It's really across the length scale, and likewise, same for materials properties. And so we knew the correlations between B and C effectively were strong. And what we wondered with Professor Rapp's team is, could we devise a descriptor that basically could lend chemical intuition into the structure? And so this is exactly what our colleagues did with this descriptor. And so we call this the charge separation descriptor. And so let me walk you through this schematic. So basically a CSD value, we first define a plane that comprises 2 lead atoms. And then we measure the distance of the ammonium. So each of the three hydrogen atoms and also the nitrogen, the distance between that atom to the plane that we define. And we multiply that by their Bader charge. So just think of a Bader charge as a volume of charge around an atom. We divide through by their Bader charge and we end up with a CSD value in angstroms. And so the way to read CSD going forward is if you see a high number in CSD, that means that the center of charge of your ammonium is withdrawn from that A prime site. And if you have a lower CSD, that means that this ammonium group that's attached to each of the ligands is really penetrating deep into that A prime site. And that gives it more of an opportunity to interact with these equatorial positions that I mentioned earlier. So obviously we have a boundary around the CSD value because the organic ligand and the inorganic framework have to interact in order to maintain 2D assembly. So it's not that it can be infinitely far away or also conversely infinitely close. And so the first question we asked ourselves is, can our descriptor correlate to structural properties? And so here I'm showing on the x-axis our CSD value, and I'm showing those two structural properties that I've mentioned a few times. So again, the lead-iodide-lead angle, and then also the interlayer spacing. And so what we see in our CSD value is that as our CSD value increases, and so in this point here is our cyano case, again, it correlates really strongly with the fact that our cyano is almost very close to that 180 degrees. And also it has the smallest interlayer spacing. So our CSD value is really, really good at, on the molecular scale, being able to lend intuition to what's happening to build up structure, which matters to us because structure, as I've shown earlier, correlates really strongly to materials properties that serve as inputs into devices. We also were curious, the ligands I showed before are all alkyl based. So we also ran these correlations with ligands that were nothing like alkyl based or had more than one ammonium. So here I'm showing a diammonium that we call BDA. And then we also did a couple of aryl ammoniums. They're much more sterically encumbering than these alkyl groups to see how robust our descriptor could be in correlating with the lead-iodide-lead angle or that octahedral tilt. And so what we can see that our descriptor is really good at being able to correlate to that tilt angle, as you can see here with that R squared of 0.96. The interlayer spacing one is less strong, and we believe that we have a good hypothesis for that. And that's largely that as you think about interlayer spacing, it also has to encompass the sterics. And so these molecules, because they're bendy, can contort in different ways. And so the spacing is a bit more problematic for correlations. And so with the hypothesis, again, our hypothesis is, can we install MODIs on these purple circles? And can we withdraw our organic ligand away from that inorganic octahedra? And if we do this, we've shown that results in less distortion in that metal halide metal angle. It results in lower band gaps. And also we see higher mobility. And so with that, we were really curious about how would these materials properties, if at all, impact solar devices. And so I'm showing one of those studies that we did for this talk, and this is where we did an N equals 4. So that basically means 4 of your inorganic octahedra together. And so I'm showing the JV curve, so voltage versus current, and then the EQE. And so EQE, just think of electrons per photon. And so really those materials properties, I think, are more evident looking at their EQE. So I mentioned that the higher hole mobility, as we went from our control, our methyl group, down to our cyano, hole mobility increased linearly. And so what we see here is that we're able to convert more of those photons to electrons, all else being equal for our cyano case. Likewise, our cyano had a smaller band gap than our other materials, and it follows again going from highest band gap or lowest and also lowest CSD value to highest CSD value and lowest band gap. And we can see that too in the EQE, where our cyano is absorbing lower energy light. We were excited to see that these materials are really stable under operational conditions where they have a T80, so basically saying that they're able to maintain 80% of their power over 1,000 hours. So I guess it's over 40 days. And so what that ended up resulting in is we have a power conversion efficiency, a PCE, of 16.4% for our cyano, which at the time of writing was the highest amongst N=4 devices. And so a couple of design observations off this study and how the CSD has lent a lot of intuition to us in terms of how to develop even other ligands and other material systems for 2D perovskites is that we've learned is that the cyano case was able to make this nitrogen atom much stronger intermolecular interactions with the ammonium than even the hydroxyl. So we think there's something to installing a nitrogen atom more so than the hydroxyl. We also note that the geometry of that non-ammonium terminus also mattered, where you have a cyano that is an sp, or just imagine a triple bond, versus in our alcohol case here, it's just a single bond. And why I think for me that I've thought a lot about this and why it seems to matter is that if you imagine in your 2D assembly, you have your non-ammonium terminus and your ammonium terminus. They are trying to do two things. So your ammonium needs to coordinate to your inorganic octahedra, but it also has this opportunity energetically to make a cross-organic bilayer interaction. It's kind of a tug of war for that ammonium. But if your cyano case has the exact same tug of war, it really also wants to go across the organic bilayer and make that hydrogen bond. But this SP geometry basically limits how much of contortion it can do. So the ammonium really has to do a lot of the heavy lifting. And that's why I think it affords this C shape, really withdrawing it away from that A prime site, and why in this ammonium case, it doesn't interact with these equatorial iodide positions. So ultimately, we also then know that the size mattered. So I mentioned the molecular zipper earlier. So relative to our control, that material system was really nice. But I do think that there's something to forming these dimer units in these 2D perovskites. And so again, our goal is how can we take these design observations and design next generation materials, which is an ongoing research area in the LU group. So the second story I'd like to share is about targeting markets silicon cannot easily access, and that's through organic solar cells, so transparent organic solar cells. And so the big picture of the story and where I come in is thinking much more about these organic absorbers. So solar cells are going to be composed of the bulk heterojunction of a donor material and an acceptor material. And so what kind of properties do we want to endow our organic absorbers with in order to use them in solar cells? And so here I'm showing a schematic of a solar cell that is not transparent. So the top electrode, which I've shown with these gray bars, is in our case aluminum. And so then once we get working OPV devices, then the optimization is how can we replace these aluminum electrodes with a fully transparent device? And so why transparent solar cells are important, or how could they be important going forward, is that you can imagine directly integrated applications. And so one option, you could imagine something that maximizes aesthetics, so really high transparency and high color neutrality, and requires low power. So electrochromic windows would fit this type of application, or Internet of Things displays. Another application that slightly differs in terms of that trade-off with that I'll mention in a couple of slides about transparency and power is building integrated PV, where you can imagine a solar coating that could absorb the sunlight, and you could use that absorption and use that sunlight to turn into electricity to help power or offset some of the energy cost of your building. Obviously, all of these technologies and the application readiness of this would really need to think about the energy payback and also the economics. But our job as researchers is really looking about, can we create these materials? And so in order to understand that trade-off and which versus power versus aesthetics, there's a couple of things I'd like to share. So one of them is the interfacial offset. So if we think about where power comes from in a solar cell, so the power conversion efficiency, we have a voltage, we have our current, and a fill factor. So this voltage term is really set by the interfacial offset. And so that would be, if you look at my schematic, the HOMO of our donor, and then the LUMO of our acceptor. So this is called the PV gap. And that is something that we'll mention in a couple of slides that was really important for us. The current, so the second parameter that I mentioned, is really largely set by the absorption of our material, so our donor material and our acceptor material. And so if you're trying to create transparent devices, you need molecules that are not absorbing visible light. And so we have two options. We have the near UV space when I look at my spectral irradiance on the y-axis versus wavelength, or we can look at the near IR space. And so you can see that and you can imagine, or for spectral irradiance, think about that as power density per nanometer per lambda. So if we have in our near UV space, we have all else being equal, less power, or less of a power budget available to us, but we're able to design materials that can closely have an onset that doesn't go too much into the visible range. In the near IR space, our power budget's higher, no doubt. However, it's really difficult synthetically to design organic materials that have no absorption in the visible range. They're going to be bleed somewhat into that space. We were really interested in maximizing transparency and color neutrality for our devices. So we wanted to design molecules that absorbed in the near UV. And so the question we asked ourselves is, well, what kind of materials properties do we need? So my colleague, Dr. Quinn Burlingame, published this really nice paper that I've put here at the bottom. And what he really was interested in understanding is that trade-off in transparency versus power. So on this left plot here, think of your APT as a measure of transparency. So the higher your APT, the more transparent your device is versus power. And what he learned from this, as you can see, each of these colors represent a certain wavelength cutoff, is that you really trade no transparency until you start reaching about 440 nanometer cutoff. So there's no point in me designing an organic absorber that has onsets that are less than that, because basically I'm just going to create something that's lower power, but it doesn't benefit aesthetically. So that was a really key input into our design process. Likewise, our color rendering index, so think about this in terms of the higher that number, the more color neutral your device is going to be. He saw a similar picture that, again, your CRI, up until about 440, you really are taking no cut in it. And so really thinking more about, and you get more power. And so what we learned from this simulation paper is that we wanted to target organic absorbers that were really strong absorbers. So we needed that, again, because what I mentioned on the previous slide is that the power budget in the UV range is not a lot. And so we need these materials to get as much of a piece of the pie as they can there. We see the cutoffs around 420, 440 are where we want in terms of maximizing the power that we need for these application integrated technologies without sacrificing aesthetics. And we were targeting the white point, which is 0.33 for highest color neutrality, which he shows here in this plot. And what we learned is we knew we were going to have, regardless, really thick active layers in order to absorb as much as we needed to create good solar cells. So with this knowledge, we went through a really nice design process that we used a lot of chemical intuition, and we used a lot of density functional theory to model about 20 potential absorbers that we wanted to use in these for these devices. And so, a very long story short, here is what we found. And so the diamine is the molecule that we decided to go with for stability reasons and modular reasons. And so it has these two nitrogen atoms that are in this trans relationship that are appended each with a fluorine and a phenyl. And we wanted to create two series, and their goal was we wanted to modify absorption and also maintain the PV gap across all of 5 molecules. So again, when I mentioned earlier, that HOMO and LUMO offset. And so in series 1, the oligophenylene series, we created 3 molecules. And so the N means how many copies of a phenyl unit here am I going to install between those nitrogen atoms. So if we had 1 phenyl unit, we called that DPP for phenyl. If we had N equals 2, the B means biphenyl. And if we had N equals 3, we have a terphenyl. So 3 single bonded phenyl units between these nitrogen atoms. We likewise wanted to create an acene series. So this naphthalene group or this this anthracene group also in between these nitrogen atoms. Before we went into the lab to make these molecules, I simulated what they would look like in terms of the absorption profile based off the simulation results. And what we saw was that if you look at the black dashed line, which is the phenyl, which is really our control, and we compare the two series. So first look at the black versus the pink. So we have our phenyl, and then we have DPB. I'm sorry, let's do the blue. So the biphenyl and then the terphenyl, we can see that we progressively are moving our absorption out to lower energy light around the cutoffs that we found from our simulation paper. And we're also increasing oscillator strength. The picture is really similar in the acene series. So again, looking here at this pink versus the lighter pink here. And we saw that compared to one phenyl, when you move to two fused phenols or three fused phenols, we can increase our absorption to lower energy light. And so with our molecules, what we first wanted to understand was how close were our simulation predictions and our DFT. So we teamed up with Hannah Smith and Antoine Kahn's group here at Princeton, and they measured the HOMO and LUMO energy levels using UPS and IPS. And what I want to draw your attention to is, again, that PV gap that we were really interested in, is that all of the HOMOs of our molecules were largely invariant. And so we paired this with B4PY-MPM, which is a commercial acceptor in the organic solar cell space. And so it had a LUMO energy of minus 2.9. So we can see that our PV gap there was about 2.3. We see that our goal of modifying absorption also was true, in particular in the acene series, where if we imagine our one phenyl here is DPP and has a LUMO of minus 1.9, we progressively move our LUMO to minus 2.1 and minus 2.4, so also increasing absorption. And you can see here by the DFT generated orbitals, what I have is that the highest occupied molecular orbital is largely comprised of a pair, the lone pairs situated on your nitrogen atoms, while the LUMO is moved to the linker. And so then we, looking at the experimental absorption, we see it looks very close in agreement to what we simulated using DFT, where we can see that compared to DPP, which is this gray spectra here, we can see that each of our molecules are progressively to lower energy light, and we also can increase our oscillator strength. So with the molecules in place, we tackled our absorbers. The next part of our project was, well, let's see if we can make working devices with these molecules. And so here I'm showing first the non-transparent devices that we made. And that means we used an aluminum top electrode of 100 nanometers. So I'm showing the JV plots and also the EQE. And so the main takeaway, I know there's a lot of data on this slide, are that from these 5 different heterojunctions, what we decided was that we wanted to choose the 3 that we have highlighted in gray to carry on to the optimization of our transparent solar cells. We ruled out our phenyl that I mentioned earlier, and that was largely because it was absorption limited, and also that was reflected in its current that was much less than our other materials. And we ruled out our anthracene case because of, you can see in particular in the JV plot, it's the green spectrum here, is that it was voltage dependent photocurrent. And so we believe it has pretty significant charge extraction issues. So with these 3 materials, a very long optimization process on the ITO electrode took place, and in order to create a fully transparent device. And so I'll show the end results of that optimization process. And so I'm showing the device architecture here. And so again, we use an ITO 40 nanometers as both our top and bottom electrode, the JV plots where we can see all 3 of our devices were working devices, and then the EQE. And we manufactured this architecture both with an aluminum top electrode to basically to have a control. So this is an inverted architecture that we hadn't tried before, versus a transparent. So we wanted to basically see how did our device parameters change just by changing our top electrode. So the aluminum will not be transparent, and then the ITO is transparent. And we were extremely happy to see that a lot of the hit we took really came out of current, which makes sense because when you have an aluminum top electrode, what happens is that you have a second pass of absorption for your organic layer, because the light coming into your device will reflect off that aluminum top electrode, giving your organic absorbers a second time to absorb. Without having a opaque electrode, when you have an ITO top electrode, you don't get the second pass. So we should see that our currents decrease, and they decrease by the magnitude that we would have expected. And so all of our devices were working devices, and we yielded power conversion efficiencies that I have here on the right. And so then again, thinking about that power and aesthetic trade-off and using an outcoupling, TPBI outcoupling layer, I'll walk you through our lab. So the transmittance is on our y-axis and wavelength on our x. And here, this dashed black line here is our photopic luminosity. And so the way to think about this is how our eyes, human eyes, can perceive color. And so if the visible range for color is 400 to 700 nanometers, what this is showing you is that we're really good as humans at looking at green light. So we perceive that very well. And so what we optimize these devices for in the outcoupling layers, could we put the peak of our transmittance at the peak of where our eye is most sensitive? And as you can see across all three devices, we were able to do that very easily. And this transmittance is showing how much light can be passed through your device. And you can see we have a bunch of light that's being passed through, and that really comes through in our APT. And so our APT values are 80 to 82, which are extremely good, and they're actually the highest of transparent solar cells to date. So we see the APT versus power trade-off here, where we can see our devices, which we have here in these nice colorful circles, is that we have a really high APT relative to the other state-of-the-art that have been synthesized and fabricated thus far. So a metal halide, and then also an NIR absorber. And the trade-off really comes through, and I guess I should also say there's no such thing as a bad transparent device. It really is your application limited or application demand. So this NIR absorber, it makes a lot more power than we can make, but it sacrifices aesthetics. So we're really color neutral here. And that comes through in our CRI, where you can see we have the highest CRI of the two that I just mentioned. And the trade-off with that is the power. So as long as your solar cell can produce enough power for the application you intend it for, with the aesthetics that you're optimizing, then that is a good thing. And so each of these devices that we have made are essentially colorless. It's really neat in the lab to see through them. It's really crazy to see how transparent they are and color neutral they are. And there are records for both their APTs and their color rendering indices as well. So with that, I hope I've been able to show you some of the emerging technologies that we're thinking about here in the laboratory at the Andlinger Center for Energy and the Environment, and how exciting it is to be in this field at this time. And really, I think it has to come back to like why, this call to action. So whether we're on the economic side of this, we're on the science side of this, so many of us here are thinking about the fact that we have 7.8 billion people globally consuming resources. And we still have a huge proportion of people on Earth that do not have access to electricity. So that's a problem and needs to be rectified. And then we have, an increasing amount of population that's predicted over the next couple of decades. And all of these parameters mean that when we started this talk about CO2 emissions, is that energy demand is going to keep increasing. And so our job as researchers is to think about technologies that we can help in some way to try and mitigate these challenges ahead of us. And then no one single technology, I believe, is the panacea for our environmental future. So whether we're thinking on broadband absorption technologies that can supplement silicon, or these more niche technologies that can help drive locally integrated displays and technologies, all of it's needed, and it's a wonderful field to be in. So, excuse me, with that, I really must thank my advisor, Professor Lynn Liu. She took me into her group as a synthetic chemist and gave me the opportunity to learn a lot about devices. And on the Organic Solar Cell project, I mentioned Quinn, who has been a wonderful mentor, and he's a wonderful device architect or fabricator. So he's been the one that has taught me almost everything I know on that side. And then Xiaoming and I also on the perovskite side have been able to team up and create these really exciting like interdisciplinary story on 2D perovskites. Here's our group on a recent hike, and thank you for your attention, and I'll be happy to take any questions.
Thanks, Melissa. This is a great talk. I'd like to encourage the audience, if you have questions, feel free to either enter them in the Q&A box or raise your hand in the raise hand feature at the bottom of your screen, and you can ask your question live if you'd like to do that. I'm going to start off with a general question. Melissa, for those of us who aren't really familiar with 2D perovskites, what advantage do they hold over the 3D structures that you might use in photovoltaics?
That's a great question. So the main advantage that why people got interested in the community is the fact that linker that I mentioned earlier that's comprised of carbons and hydrogens. So carbons and hydrogens dislike water. And so the main challenge on 3D, their efficiencies are higher, but their stability is lower. And it's because of this water problem. So if you can have larger organic cations that are part of your 2D assembly, then the thinking is that they're going to effectively act like a water repellent. And so you could increase your stability. So the trade-off we're seeing right now is that the power of these 2D devices are lower than their 3D, but their efficiency or their stability is much higher.
Gotcha. Okay, that makes sense. In that regard, is the water tending to associate with halides in the structure? That would be my guess.
Yeah, I think there's many degradation pathways and there's a huge community that's really trying to explore that. I think also within even Professor Kahn's group as well, and then also Professor Rand here, both at the Andlinger Center. So certainly I think with the halides, it is an issue as well, but also with those ammoniums, those hydrogen atoms are pretty acidic. And so ammoniums and nitrogen amines in general can do some pretty cool, but also I guess annoying chemistry when you're trying to make stable devices.
Sure, sure. I don't see any questions, so I'll be greedy and ask another one that I've got in mind, which is looking at the sequence again with looking at the perovskites in the sequence of linkers that you chose and the carboxylic acid sequence up to the cyano group. Have there been, it looks like sort of I guess as you increase the strength of the hydrogen bond, potentially that is what's pulling together the layers and straightening out the tilt. So that made me think of potentially fluorinated organics. So I was wondering if that's been something you've looked at or other folks have looked at.
That's a great question. So fluorine-fluorine interactions are pretty hot right now. And there are several papers that have come out in the last couple of years, and in particular in the last month. So lots of people, and I smile because we're actually writing up a piece right now on halogen bonding in 2D perovskites. Because a lot of people think that fluorine-fluorine interaction is a halogen bond, and we're about to dispel that. But to your question, is like people, what they're looking at is fluorinated phenylethylammonium ligand. So having an aryl group that is completely fluorinated, and then trying to study that in 2D perovskites. And so that, if you think about, and so to not use like the acronym, so if you have that phenyl group that is just has hydrogen atoms versus the phenyl group that has the fluorine atoms. There was a paper that came out last month that showed there was a massive boost in PCE based off that fluorine. So I think you get the fact that it's hydrophobic, so stability really improves when you add the fluorines. But also I think there's something to that 2D assembly, those fluorine-fluorine interactions are also helping to drive assembly in that bilayer.
Gotcha. Cool. I see that Antoine has a question. Antoine, would you like to unmute yourself and ask the question live?
Sure. Thank you, Melissa. It was a great talk. I really enjoyed it. Again, about these, about the 2D perovskites, two things. One first, very, I guess, technological. Have you been able to control, or have you looked to control the thickness of the inorganic layer beyond 1, n equals 2, n equals 3, n equals 4. It's always an issue of getting phase pure material. So I'd like to know what your experience has been with that, with these particular ligands.
That's a great question. So we fabricated films and devices on n equals 1 and n equals 4. And Xiaoming did study their phase purity and was able to prove that our n equals 4 devices and films are phase pure. So they are strictly composed of the n equals 4 layer. We did not do n equals 2 and 3 though.
Okay. And second question, now that you're playing with these ligands, are you also thinking about more delocalized ligands and so on that would allow better communication across the plane and really change the relative gaps of the inorganic and organic parts of the material?
100%. So one of the things after we had the study, and something that I think that maybe even collaborating, teaming up on this is from our initial collaboration is, just let's say you even just had a phenyl group and you install that hydrogen bonding moiety in the para or the trans position. Could we see the same results, but having that conjugated ligand? So trying to, again, like have that out of plane transport. And phenyl groups are not the most interesting. So even if you could try like a naphthalene or something that's a bit more conductive, I think that no one's done it yet. I think it'd be a really, really nice study.
Okay, thanks. Great talk.
Thank you.
Great. I don't see any other questions, so I do have one last question for you, which is related to the transparent solar cells. Oh, wait, there is someone with their hand up. Raul Hernandez Sanchez has a question. Raul, would you like to unmute yourself and ask your question live?
Sure. Hello. Can you hear me?
Yes, we can. Hi, Raul.
Hi, Melissa. Wonderful talk. I was very intrigued about the hydrogen bonding motif, but if we depart from that idea, can you envision putting on a group that you can polymerize in situ?
I definitely can envision that. So I've thought a lot about that. There is a paper from Hima's group out in Stanford where they weren't able to get a structural file, but their idea was they took acetylenes and they tried to, I think with UV light, tried and then polymerize that. They characterized it through some materials properties, but they weren't able to get the structural file. So I wonder if there's a way, because the fact that you can have the diammonium link the two inorganic, is there a way to have something a little simpler where if you could have, imagine having, there's a couple different options where you could imagine trying to even have across the layer polymerize itself or even locally polymerize. And no one's been able to structurally characterize that, I think, with like structural evidence, but it's something that it would be really helpful in terms of that out of plane transport.
Awesome. Thank you.
Before I chime in, are there any other questions sitting out there that I don't want to ignore before we go? Okay, then I have one last quick question for you, Melissa, which is, I understand the near IR. This is for the transparent solar cells. It sounded like the near IR observers that people have looked at to absorb some of the visible light that we perceive and weren't as attractive as candidates for those types of cells. But my question was about this long-term stability of near IR chromophores versus UV chromophores, and whether there's good evidence out there. People are trying to move in that direction because of potentially enhanced stability for things that are absorbing the lower energy light as opposed to the higher energy.
That's a great question. So I guess making sure I'll understand. So the idea is that you're worried about chemical instability because of UV versus the lower energy NIR.
More chemical reactivity down.
Exactly. So we've looked at the stability of these cells, and the stability is poor on these cells, but it's not chemically related. So we did some experiments where we, from both UV and then from mass spec. So we had fresh samples, and then we shined AM 1.5G light on for several days, and we measured different data points. And what we saw is that we believe it's not the chemical stability of these, despite the fact that they're absorbing high energy photons, is not the problem. And largely, and I think in the organic space, it's morphological instability. And so whether that's on the NIR space or that's the UV space or visible space, it's a huge stability bottleneck or hurdle that as a community that we really need to tackle. And that's something that certainly that we are turning our attention to at the moment as well, not just with this technology, but just in general, because I think for OPVs to really be a part of this solution for our environmental future, stability, we're getting the performance, the power up. So for across applications. And so we're not power limited anymore as much as we are stability limited. So directly, like we wondered about the chemical instability, but it certainly does not appear to be chemical unstable despite where it absorbs. It's really a morphological issue.
Great. Well, I will catch you sometime and ask some other questions about that, because I find that really interesting. Thanks again for that excellent talk and the engaging Q&A. I would also like, in closing, to acknowledge our co-sponsor for today's seminar, Dartmouth College's Arthur L. Irving Institute for Energy and Society. And I also want to thank the staff at the Andlinger Center who've been working hard behind the scenes to support the creation and delivery of this seminar series all summer. Finally, I'd like to thank you all for attending today. This marks the end of the New Light series, and I look forward to seeing you at future Andlinger Center events, and hope you all have a great rest of your summer. Take care.